Welcome everyone. This is Jim Corkins and we are beginning our first lesson in your physics course. Okay? So if you haven't done the reading, please do so. Those readings are indicated in your Canvas course. Right? Now let's go ahead and look at our overview for the first, I would say, three chapters of our class. Okay? Developing a charge model is going to be what we're going to be focusing on in this lesson. So this is going to cover charge and charge models, insulators and conductors, okay, as well as how electrons are exchanged between objects. The next group of lessons will focus on Coulomb's law, which is an electric force and discovered by Coulomb. And then we will move on to what is the electric field between objects. All right. Now, for beginning with charge, you have to understand basic chemistry and the periodic table. You don't have to understand it in depth, but you do have to know about protons, electrons, and neutrons. All right? Now, looking at this, we have a lithium atom, which has 3 protons, 3 electrons, and 4 neutrons, if it is stable. Okay? And I'll talk about what I mean as stable in a second. Okay? Now, a stable lithium atom will have no net charge, which means for every electron, there is a proton canceling it out. Electrons and protons have the same electric charge, just oppositely charged. Electrons are negative 1.6 times 10 to the negative 19th coulombs. Protons are positive 1.6 times 10 to the negative 19th coulombs. Neutrons have no charge. Okay. Now, an electron is very small in comparison to a proton or a neutron. Now, protons and neutrons are the same actual mass. Okay. But an electron is much smaller than that. It's 10 to the negative 31st, which a proton is 10 to the negative 27th. So this is like comparing 1 pound being an electron to a school bus, which is about 10,000 pounds. All right? They're huge. Protons are huge in comparison to electrons, even though they have the same electric charge. Okay? Now, if you want to quantify the total electric charge, what you do is you count all the protons, all the electrons, and add them together. Really what was happening is you'd be subtracting. So if you have 1 proton and 1 electron, so we're going to be looking at the total charge equation. Okay. So in this lithium atom, let's say this, we have 3 protons, and we have 3 electrons right here. The blue are electrons, the red are the protons. And then you add those together, and then you multiply it by the charge of just a regular charge without sign, times 10 to the negative 19th coulombs. And that will be the total charge on this lithium atom. Okay? So since this is plus 3 and this is minus 3, this is going to be the N part. And you're going to multiply it by the charge, which is just an E. So Q is going to be equal to N, which is the total charge. You sum them up, times E. And in this case, that would be 0 coulombs. All right? So it's in balance. It's stable. Now, if a lithium ion loses an if a lithium atom loses an electron, it becomes a lithium ion. An ion is a term for it's got an imbalance. It's either got more electrons or more protons, meaning it's mostly plus or mostly minus. Okay? So this would be considered a lithium ion, meaning it has 3 protons. Okay? It's got 3 protons, 2 electrons. Don't worry about the number of neutrons. So in this case, its total charge would be plus 3 minus 1 times E. We're not going to write out the whole thing. Plus 3 minus 2, I should say. And so this charge right here is going to be a positive times 1.6 times 10 to the negative 19 coulombs. Okay. Now, this is another type of ion when it has caught an extra electron. So now it's got 3 protons, as it always has, and it's got 4 electrons. So in this case, you're going to go ahead and sum that up. It'll be plus 3 minus 4 times E, which is now going to be negative 1 times E, which will be negative 1 times 10 to the negative 1.6 times 10 to the negative 19th coulombs. Okay. It is possible for these atoms to lose all of their electrons. Okay. And in our class, we are not going to consider situations where the proton gets kicked out of the nucleus. Okay. That is a whole other deal. In our class, we're going to consider only the electrons moving on and off an object. Okay. So if something becomes more negative, it's because electrons are jumping on it. If it becomes more positive, it's not because positives are jumping onto the atom. It's because electrons are leaving the atom. So in this case, the most positive this lithium ion could be is plus 3. Okay, it could never be plus 4. All right. So that is the basics of how charges, electrons move on and off objects. Okay, so basically you have to, in our class, only electrons move, protons stay where they are. Okay, so that is this rule right here. If something is negatively charged, it can drop even more electrons. All right, let's test out what you just learned. All right, so here we have a concept question. Okay, we have an atom, and we have 3 different atoms, and your job is to identify the total charge, which in this case we're just talking about N. We don't want to worry about the times 10 to the 1.6 times 10 to the negative 19 coulombs. But the total charge in this case, so you're just counting protons and counting electrons, adding them together, and that total is what I'm asking you to do. The protons are red and positive, and they're in the nucleus. The electrons are blue, and they're on the rings. So try and find out the total charge of each one of these atoms. Please pause the video now. Okay, we are back here. So I'm going to count the number of reds in this first one. I'm seeing 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be positive 8. And then I'm seeing 1, 2, 3, 4, 5, 6. Minus 6. So I am seeing positive 2. So for the total charge here, if we want to consider N, this would be plus 2 times 1.6 times 10 to the negative 19 coulombs. So in other words, this would be, what is that, 2, so that's 12, so that's 3, positive 3.2 times 10 to the negative 19 coulombs. All right. I just wanted you to do this first part. All right, so for this next one, the middle one, I'm seeing a positive 4, and I'm seeing a 1, 2, 3, 4, 5, 6, minus 6. So this would be a negative 2 total charge. Again, that would be a negative 2 times 1.6 times 10 to the negative 19 coulombs. Really small number. So in this case, it would be, the total charge would be negative 3.2 times 10 to the negative 19 coulombs. All right, for this last one, I'm seeing 1, 2, 3, 4, 5, 6 protons. And I'm seeing 1, 2, 3, 4, 5, 6 electrons. So this is 0. So this charge, total charge on this atom would be 0. Okay? All right, so hopefully you understand the concept of net charge and how to calculate net charge. Let's move on to what makes something a proton, an insulator, and a conductor. Okay. Insulators and conductors are wildly different in that in insulators, the use is if you dump electrons on an insulator, where you dump the electrons, they will stick right where they are. So they will not move from this area right here. If you took a negative metal rod and dumped it onto a rubber object, those electrons would move how much they could fill right here, and they would stay right there. And that's because the valence bonds are tightly bound, okay? And so these atoms are essentially separate from each other. So just to summarize, electrons are, insulators are materials where the electrons are not free to move. The electrons are stuck wherever they're dumped off. So if they're dumped, they will stick to these atoms, and they will not move off of these atoms. All right? Now, conductors are different. If you take electrons, so this is a metal sphere in this case, and you take that same negatively charged metal rod, and you touch it against a metal surface that can conduct electricity, what happens is you see those electrons go onto the metal object and they get as far apart as possible. And that is because, like charges repel, and so they will move to the outer edge of a conductor. And that is because electrons are free to move. And they are only loosely bound to their atoms. In fact, the entire object is considered the valence bonds, the outer valence bonds between these atoms. So they're not very, very tightly bound to each other. Okay? And so these electrons are free to move, to hop from atom to atom, wherever they want to go. But likely they will be moving to the outer edge of this object. So in insulator, the electrons are not free to move. They will stay where they get dumped onto and stay to those atoms. But with conductors, those electrons are free to move, and they will hop from atom to atom and get as far away from each other as possible. Okay? Now, let's look at how this affects charges moving on and off objects. Now that you understand how to calculate total charge, let's talk about how electrons move on and off objects. All right. So there's one way that you can move electrons from one object to another one, and that is with friction. Okay, so we've all been little kids. We had our little onesies at home with the little rubber soles. Or you've ever walked into a house that has a new carpet and you've rubbed your shoes against the bottom carpet. And what happens is you collect electrons and you're able to shock something, right? Well, that is called charging by friction. So whenever you rub objects with each other, there is a chance that they will exchange electrons, where if you have two neutral objects, in this case wool and a piece of plastic, something rough and something relatively smooth, they're both neutrally charged right now, right? They're not shocking anything. But if you rub the wool against the neutrally charged rod, what happens is you're ripping electrons off that neutrally, off the wool, and now the electrons are stuck, the extra electrons are stuck on that smooth object. Okay? So now the smooth object will now be negative, and the wool object will be positive. So again, electrons are the ones that are being exchanged. The protons stay where they're at. And what you're doing is you're ripping the electrons off, in most cases, like almost all cases, the rough object, and those electrons are getting onto the smoother object. Okay? And so that is called charging by friction. So let me show you, there's a little simulation I could show you that illustrates this. Okay. So here we go. This is a PhET simulation. We have a wool shirt, and we have a balloon. Okay. Now, so the balloon is relatively smooth in comparison to the wool shirt. So what's going to happen, again, notice the protons in this case are going to stay where they're at. It's the electrons that move from the rough object onto the smooth object. So if you start rubbing it, it's got some sound effects. I've collected those electrons onto the balloon. And now, if you notice, since the balloon is a conductor, where I gathered those electrons is where those electrons will stay. If this was a metal balloon, the electrons would be aligned on the outside. But since this is an insulator, where I rub them, the electrons are sticking right there. Okay? So this is called charging by friction. Okay? Now, something interesting happens when you take this balloon and you bring it close to this wall. So this wall is also electrically neutral. Now notice there is a lot of charges on here. And I'm going to bring this balloon close. Now the wall is also an insulator, so the electrons can't really leave their atom. But what they can do is kind of lean a little bit. So watch what happens when I bring this close. Look at the electrons trying to get away from this balloon. And notice that the balloon is attractive, right? So when you were a little kid and you were in science class, you had your hair and you had a balloon, and you rubbed your hair against the balloon, and your hair is rough, the balloon is smooth, and now those electrons are bound to that balloon. And then when you put it up against the wall, which is neutral, it sticks to it. Okay? So notice that the electrons in the wall are moving away such that these electrons are closer to those protons, which means they're just a little bit more attractive than these electrons repelling these other electrons on the balloon. So, and I would imagine that these electrons in the balloon are also trying to lean away as well. So, I'm going to turn this off. It's distracting. It's very whimsical. I like it. But the wall is neutral, and this balloon is sticking to it because these electrons are just a little bit closer to these protons. And these electrons are just a little bit further away from these electrons, so their repulsive force is a little bit smaller, such that the balloon is able to stick. And that is the beginnings of the Coulomb force. Okay? So notice how the balloon, being negative, is reorienting the atoms in the wall. where the electrons, again, are the ones that are moving and the protons are staying where they're at. Okay, so let's go back to our presentation and let's ask you some questions based off of what you just learned. Concept question number 2. So here we go. We have a hydrogen atom. It's got a proton and an electron. And we have a hydrogen ion where it doesn't have an electron. It's just the nucleus. Now, those are the two objects. They are separated by a distance. When we let these go, okay, what will happen based on what you just learned with the balloon simulation? Will they attract, repel, or will they not experience a force at all? Pause this video and try to answer this question. Now, before we answer it, I want to ask you another question. So, same situation, you have a helium atom that's neutral, and you have a hydrogen atom that's neutral, and a hydrogen ion that is just positive. When we bring this hydrogen ion closer, these two objects are getting closer to each other, okay, what is going to happen with the hydrogen atom? What will happen? Will it look like A, where nothing happens? Will it look like B? Will it look like C? Or will it look like D? All right. So pause this video and try to answer this question. All right. Let's go back to our very first one. So from what we had learned is that when you bring this, right now, this neutral atom is experiencing a force that is attracted to this hydrogen atom. So, this hydrogen atom is experiencing a force with this hydrogen ion. This proton is attracted to this neutral atom. And that is because this neutral atom, so they're going to begin to attract that. So the answer is B. And they're going to being attracted, and that is because the atom, the neutral hydrogen atom, has reorganized itself such that the electron is now just a little bit closer. So look at this distance. It's a little bit closer than this one. So this distance x is greater than r. And yet they are repelling, but since it's that further distance away, it's not repelling as much as the electron is attracting to that proton. Okay? So this is our beginnings in understanding the Coulomb force, which we will explore in the next videos. All right. So just like if we had a negative guy and we had our proton, so this is the hydrogen atom again, and we just had a random negative charge here in outer space, they would also be attracted just like we saw in the video. And that is because this negative guy is going to try to get further away from this negative charge. So you would see if you brought this closer, you'd see this negative guy switch to the other side. So now this distance r is just a little bit closer, so it's going to be a little bit more attractive than this distance x where they're being repelled from each other. Okay, so it works both ways. So a charged object will be attracted not only to its oppositely charged counterpart, but it'll also be attracted to a neutral object. And that is because the neutral object's electrons are reorienting themselves so that they are moving closer to or further away the charged object. Okay? Now, let's learn another way of how charges, well, we already did kind of learn this, but that is called polarization. when you have an atom reorganizing itself, okay, that is polarization. So when you bring, again, you have that positively charged object right here, and you bring a positively charged object closer to, the electron is getting closer to this positively charged object. It's polarizing the atom. Okay? And if it's a negatively charged object like we just learned, that negative is going to be way out here. Okay? So what's happening is the neutral atom, or, well, the atom is polarizing itself such that the electrons are moving towards or away from the charged object. Right? So that is called polarization. Now, let's do another concept question. And so this is about, again, understanding electric charge. To the right, you have two objects that are repelling each other. Okay, they're hanging from the ceiling. They would normally be hanging straight down. Okay, like this from the ceiling. And that's if they were both neutral. Okay, so a neutral atom, where two neutrally charged objects don't really do anything. They don't attract or repel. They just don't notice each other. Okay? But these two objects up here are charged. Okay? And they're repelling each other. What sign do they have to be? Do they have to be the same sign, meaning plus and plus, or minus and minus, or oppositely charged, meaning plus and minus, or they're both neutral? Obviously, they're not neutral. But pause the video and answer this question. All right. So if these two objects are repelling each other, that means they are pushing away from each other. Okay. So this is a little mini force diagram. And so what that means is they have to both be the same sign, both positives or both negatives, because same signs repel, opposite signs attract. And a charged object will attract to a neutral object. So those are the rules. Okay? Let's try another one. Normally you have this ball that's just, it could be charged or uncharged, you're not sure, but this ball is just hanging down right here. Then you bring a positively charged rod close to it, and so this ball swings up to here. Okay, so this positively charged object, this ball swung up to here towards this positively charged object. Okay, if that's true, okay, then what does the charge of the ball have to be? Does the ball have to be positive? Does it have to be negative? Does it have to be neutral? Positive or neutral? Or negative and neutral? So go ahead and pause the video now and make a choice. Okay, so we know they're being attracted to each other. So we know their forces are attracting each other. Now what that means is that this can be just an object with a bunch of negatives on it, where that would attract. So it could be negative, but also it could be neutral. Meaning if this is a charged object and the positive is here, that means the negative will be on this side. The negative will try to align itself to be closest to this positively charged rod. So the answer is going to be negative or neutral. Okay? I hope you're doing well on this. I'm sure you're doing well. All right. So here are the rules and tactics for drawing a charge diagram. So there's a couple overall conceptual understandings that we have to agree on here. So first of all, the total electric charge of the universe is constant, meaning protons aren't really created in our little physics universe that is our classroom. Electrons aren't really created. They're already existing. Okay. So we're not going to be creating electrons, creating protons, creating neutrons. Okay. So electric charge is conserved in our classroom. Okay. Now, oppositely charged objects attract, like charged objects repel, and neutral objects will attract to charged objects. That's not to say that a neutron will attract to a proton or electron. A neutron wouldn't even notice a proton or an electron. But what I mean by neutral objects is they contain positives and negatives. For if we had 3 positives, like in a lithium atom, then we'll have 3 electrons, and that will be a neutral, stable lithium atom. Again, if you want to figure out the total charge of an object, you've got to add up the protons and electrons and then multiply them by 1.6 times 10 to the negative 19 coulombs. 2 objects that touch each other, they will exchange electrons until these 2 objects will be equal in charge. And we'll get into that, how that actually happens. And again, it's the electrons that are moving on and off objects, not the protons. If an object has lost an electron, it is now positively charged. If an object gains an extra electron, it is now negatively charged. Okay? Now, what we're going to be doing is drawing charge diagrams. All right? And these are little 2 charge diagrams. So what you're going to do is, draw circles. And then what we're going to do is we're going to put the excess charge on the outside of the circle. So in this case, this is an inductor. So where you dump those electrons, they'll stay there. If it was a metal object, you would see those electrons, and I'll get blue out here. Those electrons would spread out along the edge of the circle. Okay, and we are going to be dealing with metal objects in our class. Now, the interior of this atom, we would draw the positives on the interior. And if we want to draw neutral atoms there, we would then tag on an electron to those atoms right there. Okay? So what we're going to be doing is we're going to be playing little games about how electrons are jumping on and off objects. And again, when they touch, meaning they're connected by a metal wire or the actual 2 spheres do touch each other, that's when they exchange electrons until they are equal in charge. Okay? Now, for the transfer of charges, I got this from a textbook. We want to be careful about how charges are transferred. So this is a metal object. So we're going to draw little positives here just to be a little accurate. You can just draw a couple. You can draw as many as you want. Just don't make it too busy. And when you dump these electrons on this object, so I'm going to just put 4 protons in each one of these things on the interior, just like we did the other object. And then we're going to draw little negatives attached to those. So these are neutral atoms. So now this metal sphere is neutral, but you've dumped a bunch of electrons here. Now, since this is a metal object, when you dump them there, they'll be there for an instant, but then they will quickly spread themselves out on the outer edge of the object. Now, here's a problem with charge diagrams that do not include neutral objects. So here we have a metal sphere that is completely positive, and we have a human being that is neutral. Now, I think one of your textbooks says don't draw the neutral atoms, but I'm arguing you should, Because when you look at this person looks like they're uncharged. And then in the next instant, they touch the metal object, and it looks like from this picture that the positives jump on the person. Okay. And then this person who is connected to the ground, now those positives disappear. That is very confusing to me. But what they're trying to say here is that this person has a bunch of positives and a bunch of negatives on them. Okay? And what's happening here, and I drew 1, 2, 3, 4, 5, 6. 6. So 1, 2, 3, 4, 5. 5, 6. So there's 6 here. So what is happening is this person's electrons are flowing out. They're leaving this person. So this guy, this positive here, five, 6. So these negatives that are here on this person are now going to start leaving. So this negative right up here, I took out a proton there. That negative is going to jump down onto this object. This negative here is going to jump. Well, you get the idea. All these little negatives are going to leave the atoms that they were stuck to and begin binding on this person, on this object, where now we had all these negatives that were bound right here, but a bunch of these negatives jumped onto this atom, okay, and now what happens is we now just have a proton by itself. Now, what has happened to this person over in this picture, where they had 5 free protons that were not bound in our picture, okay, and 1 bound neutral atom, is the ground, because this person was attached to the ground started putting electrons and forcing electrons to neutral. Since the ground is neutral, it forced extra electrons to jump up on this person to become neutral. And since this person's not touching this object anymore, all the extra electrons, which is not showing, or extra atoms, which is not showing here, 4, 5, are actually still there, but with their neutral, they're in a neutral state. So what they do is they say in this neutral state, you're basically erasing those neutral atoms. But I say leave them there, because that makes more sense to me. Because the picture that we had before, it did look like the metal objects, positives, jumped onto the person. And really what the case is the electrons from the person jumped onto the metal object and pairing up with those extra protons and making them neutral. Okay? And then the person who lost their electrons, the ground flooded that person with electrons and made them neutral again. Okay, that's what we're going to be doing. So we're going to be practicing that. Okay. So there's something else that we have to learn, which is called charging by polarization. So we went through charging by friction, okay, and then we went through the transfer of charges. This is called charging by polarization, where you take a charged object close to a neutral object, and those electrons in that neutral object will polarize, meaning they'll get closer to or further away from that charged object. In this case, the metal rod, the electrons will get closer to that metal rod. Okay? And And what you see is that that object now becomes polarized. And then what you can do is you could then touch this metal object, and these electrons will move on to another object that maybe has some free protons. So we have another cool simulation that we could look at, and this is regarding charging by polarization. Okay, this is the electroscope here, and just off to the side, if you click on this, this will get you to this JavaScript. Okay, so in this case, we have this is an electroscope, meaning the leaves will separate, and the higher these leaves separate, the more charges are built up. So here's what I'm saying. So this is all one piece of metal, okay, and these two leaves are metal leaves. And when we bring this positively charged rod close, what do you think is going to happen to these electrons up here? Well, they're going to try to get closer to this positively charged metal rod, but these electrons are also going to flood up here and try to get as close to that metal rod. So watch what happens. The closer I get, notice that the electrons are rising up and getting as close as it can. And now you notice that these two leaves are separated because these positives are repelling each other. So the more that they're repelling, the more that you're seeing same sign charges are repelling each other. Okay. Now if I move this away, the electrons will, because they're built up here, they don't want to be together. They'll go back down and try to get as far away from possible. Okay, so this is called charging by polarization. You could then grab an object and see those electrons will move on and off this object, right? So I'm going to restart this whole thing so you can see what I'm talking about. I think you have to just reset the whole thing. So we're going to take a positively charged object. See, this person is metal, which is their hand. They're connected to ground. So notice when they touch it, because they're neutral and this is neutral, they're not transferring charges. But if you take this positively charged object right here and you bring it close, okay, now this person, their hand also has a bunch of electrons that are bound to their protons because they're neutral. Now, when this person touches this, what's going to happen is their electrons are going to build up and try to get as close to this positively charged object as well. And see, now this has a tremendous amount, a lot more. Now this object is not neutral anymore. If I remove the hand and I pull this away, now this object, which is now electrically negative, its leaves have separated. So charging by polarization leads into this other concept called charging by induction. Okay? And that's where you have two objects that are neutral, and you get the electrons to move closer or further away, and then you touch it and you rip the electrons off of another neutrally charged object, and or you take electrons from the neutral object and put them to the neutral object, and then separate everything, and now you have an imbalance of charges on the main object. So we're going to go back to our simulation. So I've reset this. Here's what happens if we have a negatively charged object. You bring it closer and you see these electrons that are up top get pushed down, and notice it's separated, and they're both and this is still neutral. Now if I pull this away, notice those leaves fall back down to where they're normal. But what do you think is going to happen if I bring my hand here? So what's going to happen is these electrons are going to be exchanged. They're going to leave this area because the electrons are trying to get away from this rod. So they're going to have an opportunity to connect and go through this person and go into the ground. Now if I separate this and separate this, now it's imbalanced because its electrons have left. And this is called charging by induction. It's charging by polarization, but also charging by induction. Okay. So again, those electrons are brought close, and I can't transfer it back. Now, something interesting happens. Since this is in balance, and I told you the one rule is the electrons need to be exchanged until they're both the same charge. Well, now this thing has doesn't have enough electrons. It's got 1, 2, 3, 4, 5, 6 protons that don't have electrons. What's going to happen is when I bring this hand, it's going to transfer electrons back to this. This neutrally charged hand is going to transfer its electrons from the ground through it so that now it's neutral and the hand is now neutral too. They're the same charge. Okay, so that is charging by induction, where electrons are moving back and forth until the two objects are the same charge. Okay, or you could transfer charges on and off objects so that one object has more electrons than, or more protons than another. Okay, and so you can't, since you can't destroy protons and electrons, you have to play this game of figuring out how to get electrons off that object, or how to get more electrons on this object. And this is how you do it. You do it through polarization, and you do it through induction. Okay? We will practice all of these things in our tutorial. But before we do that, let's see if you understand the concepts of this. So let's go to our conceptual question. Okay, so here you go. You have two metal spheres that are both touching each other, and they're both neutral. Okay, and a charged rod is brought near to the left-hand side of this metal sphere. Okay, then it says the charged rod is then removed and the spheres are separated. After a while, afterward, the charges on each sphere are going to be where Q1, this will be positive and this will be positive, or object 1 will be positive and object 2 will be negative. Object 1 will be negative and object 2 will be positive, or object 1 is negative and object 2 is negative, or they're both neutrally charged. So again, what you're doing is you're bringing a positively charged rod near these two metal spheres that are neutrally charged, and then you're removing the rod, and then the spheres are separated, and you're asking, what's the charge on these? So pause the video and see if you can answer this question. Okay, let's try this out. What I'm going to do is I'm going to draw some extra protons here. So imagine this charged rod is not even close, close to these two objects. And I'm going to just draw 4. For some reason, I'm liking 4 today. So here we have the electrons, and they're both neutral. So for every proton, you have an electron. Okay, so now they're both neutral, and the rod isn't even close. I'm imagining right here, the rod is not even close. And they're just hanging out. They're not exchanging. They're both the same overall charge, so they're not exchanging any electrons to get them equal. They're already equal. But when you bring this rod close now, what's going to happen is these electrons are immediately going to snap up, get really close to this guy, 1, 2, 3, 4, and these electrons are going to transfer through and build up on this side as well. So now we have overall, we have on this object, we have plus 4 protons, and I should color coordinate this, and this is while the rod is still near. So we have plus 4 minus 8. So that right now we're having a total charge on this is negative 4. And over here, this is positive 4. Okay? Now, what is going to happen when you move this rod really far away? Okay, so this is just still part A. Now, we're going to the charge rod is then removed. And when we do that, now these two spheres are touching each other, and they need to exchange electrons so that they are both equal in charge. Well, since you have 8 protons and you have a total of 8 electrons, these extra negatives are going to go back to they're going to transfer back over to here, to their protons. And these electrons, which are right here, are going to go back onto their protons. Okay? And what's going to happen is they're both going to be 0 again. Okay? So the answer to this question is E. All right. So hopefully this is making more sense about how charges are what is charging by. When we had this positively charged rod really close and these electrons here, that was charging by induction. You've actually made this number 1 object negative 4. Okay. All right. So that was charging by induction, and you can see again the electrons are moving, the protons are staying where they are. Okay, so hopefully this is making sense. Now, let's try another one. This is a little bit of a different case. So again, you have 2 neutrally charged metal spheres. So I'm going to draw the positives, the 4 positives here. You could draw 3 and 3 or 2 and 2. It really doesn't matter. And we have they're both neutrally charged. And again, right in this instant, the metal rod is not here. But now you bring it closer to this. So when you do that again, these electrons first are going to be, well, because they're closer, they're going to respond quicker. And they're going to fill in these spaces right here. And then these electrons are going to transfer through to the number 1 metal sphere, and they're going to also build up right here. Now it says the spheres are separated. So now the spheres are separated where they can't exchange charges anymore. So I'm going to draw that. And so they're both separated. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then the metal rod is now removed. So you take the metal rod really far away. Well, what is going to happen to the second object is it's going to stay right where nothing's going to happen. Those positives are just going to stay right where they were. But this number 1 object with its 4 protons, well, 4 of these electrons are going to bind to these protons as quickly as they can. And I think what will happen, the extra 4 electrons are going to get as far away from each other as they can. Okay? So now, just like before, we're going to have a plus 4 minus 8 which is going to give us a total charge on this object of -4, while this object over here is just +4. There you go. So Q1 will be negative, and Q2 will be positive. So that's the answer to this, C. Okay. Now, over here, in question number 6, what can you conclude if you have, in the last thing, you have something that looks like this? In the last picture, you have something that looks like this, where two spheres were charged by induction. What can we conclude by that? Well, why don't you go ahead and pause the video and try answering this question. Okay. Well, your choices are only the negative charges have moved, the positive charges have moved. So in this case, is it the negative charges have moved, is the positive charges have moved, or both positives have moved, or we can't draw any conclusions from which charges have moved? Well, in all cases, the electrons move. Protons are staying right where they are. Okay? So let's go ahead and try a practice of everything that you've learned. Okay? About how electrons move back and forth, about polarization, and also induction. All right? So here we have a situation where you have 3 charged objects that are all metal. One's P, one's Q, and one's R. This has an extra +6 protons. This has got a -2 newtons per coulomb charge, and this is a -1 newton per coulomb charge. Now you're going to touch all of them together so that the electrons can be exchanged and freely move. And then you're going to separate them all. When you separate them all, what will be the extra charges built up on each one of these? Okay? So go ahead and try it. All right, pause the video and try to work out how the electrons will be exchanged such that the amount of charge on each object will be equal. Okay, pause the video now. All right, so here we go. We have this has a +6, so I'm going to draw the positives here. 2, 3, 4, 5, 6, and then I'm going to draw like a couple extra positives and neutral objects, just like this. And I'm going to draw the same pattern over here. What I do for when I practice these drawings is I do the same amount of protons on each. And if there's extra protons and stuff, I just take the electrons off them. So I'll show you what I mean by this. Okay, so I'm trying to make the same pattern of protons on all of these. Okay. Now, this has an extra, so there's a total of 6, 7, 8, 9 atoms on this. So in these objects, let's make this a positive, this a positive, this a positive, and then these 3 positives. So let's make these neutrals right here. I'm going to make the neutral part on top of these guys right there. Okay, so that means we got 1, 2, 3, 4, 5, 6, and I will make this guy also neutral. So 1, 2, 3, 4, 5. Oops, I went too far. Let's make this guy also positive as well. Actually, there we go. So I got 1, 2, 3, 4, 5, 6. So that's a +6. Now this has to be -2. So I'm going to neutralize all of these. So now these are all neutral atoms. And I'm going to put the extra 2 electrons on the outer edge. Since these 2 electrons, so this is now, those are all neutral atoms, and it's got 2 extra electrons. They're going to be leaning as close to this positively charged object as possible. And I'm going to neutralize all of these right here. So 2, 3, 4, 5, 6, 7, 8, 9. So those are all neutral. But its extra electron is going to be over on this edge because it's trying to get away from this negatively charged object. So now we've got everything worked out. So this is going to be plus 6. This is minus 2 and minus 1. Now, let's say we connect them all together by a metal wire so that the electrons can flow across all objects freely. What we're going to see is these 2 electrons are going to immediately fly over and attach to these 2 protons, or the first 2 that they see. They'll attach. And this extra electron right here is going to flow across here and then across here and then attach to the first one it sees. So now what we have is we have it had an extra 3, it had 6, and it 3 electrons. The extra 3 electrons here traveled over here, and now this is going to be plus 3. And now these 2 will be neutral. But they're not equal. Since the wire is still connected, what's going to happen is 2 more electrons are going to come across. Okay? So we want to get them to where they're all the same charge. So, and then if you have a positive 3 and you have 3 objects, take that positive 3 and divide it by the number of objects, and what you will have is you will see this electron will fly over and attach to here. And now this guy is going to be a positive 1, and this is going to be a positive 2. And what you're going to see now is another electron from this guy, and I'll just grab this guy right here. It's going to fly over, it's going to travel across here, and then travel across to here, and it's going to connect with another proton, like right there. And when you do that, now all of them are the same charge. Okay? So in a way, what I did is I just took the total charge of everything, plus 6, minus 2, and minus 1, add it all together, and you conveniently get a positive 3. Since we have 3 objects, divide that total charge by the number of objects, and you get what the equal charge should be on every one of them. Now, I designed this question, so I'm going to just fill in the answer, positive 1 and positive 1 and positive 1. I designed it so that this is a whole number, but when you're talking about nanocoulombs, which is 6 times 10 to the negative 9th coulombs, there's millions of charges on this. Billions and billions of charges are built up on these objects. So I made it so it's whole numbers, but you could get fractions of that. And that doesn't mean you're going to get a fraction of an electron. It just means you're going to get fractions of total charges. Okay. All right. Let's try another one. And this is going to be our last one. So here again, we have this situation, but in this case, P and Q are touched together. So you're going to connect these 2 guys together and then separate it. Okay? And then after you do that, these two will then be connected together and separated. So let's start off and let's just draw a couple extra here. So we have a +6 right here. So I'm going to put +6, and I'm going to draw plus 3, 5, 6. And I'm going to draw just 2 extra pluses right here. And I'm going to do the same thing over here. In fact, I'm going to do it for all 3 again. And then plus, and then plus. And then I'm going to do the same thing here. So let's just draw our base working thing. I just arbitrarily was like, okay, I'm going to need an extra 2 here. I don't know if I'm going to need it. I might need more. But this guy has neutral and this guy is neutral, so that's +6. These guys are all neutrals. And neutral here and neutral here. And these guys are all neutrals. Okay, and so to start off, this will be negative and negative, and this extra negative will be over here. So now we're going to connect these two together. So immediately, again, what we're going to see is these extra 2 negatives are going to jump over, and they're going to jump over and nil out these. And when they do that, we're going to have 0 and +4. Okay. +4. And then what's going to happen? Well, 2 more negatives, right? We have 2 objects and a total of +4. So +4 divided by 2 objects, we got to make it +2 and +2. So we got to make these both +2. And to do that, 2 of these negatives have to jump over from this object to here. Okay, and so that is what we have. So now we've touched P and Q together, and they're now both +2 and +2. Now we're going to separate those, and now we're going to touch this guy to here. Okay, so this is going to be a unique situation because what we have is a +2 and -1. So what is going to happen here? Well, you have a -1 here. So right now, actually, we do know the answer to what P is. P will be a +2, right? And this is an interesting situation. So we have a +2 and a -1. Now, what's going to happen, again, is this extra negative is going to jump over here and attach to this guy. So now we're just at a +1, and we have a 0 here. All right. Now, here's the problem. We have 2 objects and 1 positive. All right. Now, like I said before, when we're talking about nanocoulombs, I'm not talking about whole charges. I'm talking about nanocoulombs. So this is negative 2 nanocoulombs. So this is +1 nanocoulombs, and this is 0 nanocoulombs, or 0 coulombs. All right. So we have 1 that we're going to have to divide by 2. And when we do that, what's going to happen is part of the charge is going to move across onto this other guy. So in reality, you can have part of this nanocoulomb. Now remember, each charge, a positive or a negative, is 1.6 times 10 to the -19 coulombs. That is the charge of one object. But we're talking about a nanocoulomb in this case, which is going to be positive 1 times 10 to the negative 9th coulombs. So which is greater, 1.6 or 1 times 10 to the 1.6 times 10 to the negative 19th coulombs, or 1 times 10 to the negative 9th coulombs? Well, obviously, this is the larger number. So what we're going to do is some of the charges are going to move back across to here. And I put this in here to illustrate that there is 10 times, this has 10 times more charges than a single charge. So some of those charges are going to move across, and what we're going to be left with is 0.5 nanocoulombs and 0.5 nanocoulombs. Now in your tutorial, we're just talking about whole charges. You won't run into fractions of charges ever in the tutorial. But in this case, what you're going to have left over is this situation. Positive 0.5 and positive 0.5. Okay? And this is your introduction to electric charges. Okay? I hope you had a great time, as much as you can. Have a good day, and I hope you enjoyed your first lecture.